What I'm going to talk about is a work on at the scale of molecular dynamic simulations. So there will be no quantum things, there will be no DDD stuff. So we are going to stick with the realm of atomistic modelization, but it will be multi-scale in time. Okay. And this is a joint work with Dany, with Tony Lelièvre at Ecole des Ponts, with Zupanshu Sharma, who was a postdoc in Berlin, now he's got a permanent position in Sydney, and with Olga, who was a postdoc in our place, and now, believe it or not, she's got a permanent position in Davos, in Switzerland. So they not only do finance, but they also do actually a modelization of snow avalanche and this kind of stuff. So it's really also interdisciplinary work between mathematical analysis, mathematical simulations, and modeling, mechanics modeling from avalanche and debris and this kind of stuff. Okay. So we are going to focus on systems at the atomistic scale. So I just put here a picture of a system in a living organism. As we all know, so if we look at the dynamics of this system, they stay a long time in one given well. So they oscillate around their equilibrium position for a long time before jumping to another configuration. And this is sketched here by this drawing here, where we have two metastable states, and the system stays a long time in one well before jumping to the other one. Okay? And so what matters are these jumps, because it tells you how drugs are going to be close by on cells, or how chemical reactions happen, and so on. And so what we are interested in is seeing all this transition from one well to another one, and not that much about what's going on here in this well. We are going to model the dynamics through the Langevin equation, so that we all know it's just with the gradient here, the V, the friction, and the noise. Okay. And of course, it's a huge dimension problem if we look at real applications. Okay. So we want to focus on long-term trajectories, because we want to see several hopping from one well to another one, and to, in the best case scenario, make statistics on this residence time. And because we want long-time trajectories, it's tempting to use algorithms that do parallel in-time computation. So what we are going to do is, time is a sequential stuff by nature, and what we are going to use is one algorithm that does parallel computation on the time interval. Okay? So we are familiar with parallel computation on the domain, on the space variable, and here we are going to do that in the time variable. And so we are going to use an algorithm which was proposed 20 years ago, which is the Parareal algorithm. The idea is para like parallel, and real because you would like real-time answers of the algorithm if you are in engineering situations. Okay? So it was proposed 20 years ago. We are going to use that algorithm. And actually, what happens is that the vanilla version of the algorithm is not stable if you apply it naively or directly for MD problem when the time horizon is large. Okay, so we are going to see that on the first slides, and we are going to introduce a fix for that, which is an adaptive Parareal algorithm. The first part of the talk will be dedicated to toy models, okay, just to understand things and to make analysis and applied math people. And then the second part of the talk will be dedicated to a much more realistic problem that we have tackled with Dany. Okay, so let me sketch the algorithm. It was proposed on a simple ODE framework. X dot is f of x. And the idea is that you have two integrators to integrate these dynamics. You assume that you have a fine integrator, f, like fine, that propagates the system over the time range capital delta t. And it's fine, it's expansive, it's your reference propagator. Okay? This is the one you would like to apply from the very beginning to the very end. This is way too expensive, and so we assume that we have at our disposal a cheap coarse integrator that also propagate the system over the time range capital delta t, but does that in a very cheaper way. Okay? And one of the reasons, for instance, is that the fine integrator propagates the system over this time range by making many time steps of very short, okay? Whereas the coarse propagator uses the same kind of scheme, Euler, whatever, but with a much larger time step, and maybe you go for the full interval by just doing one time step, okay, instead of many of them. And what I'm not going to address in this talk, but also you could think of this, is to try to use reduced model that is coarse integrator that would only integrate some of the variable of the system and not all of them, okay? This is another possibility to save computational time. We're not going to do that here, but this is also possible. Okay, so we have these two guys, and let me explain with the drawings at the bottom of the slides how we proceed, okay? So we have our initial condition here. So this is the time arrow here, and this is the phase space arrow. We have our initial condition there, and we first propagate this initial condition with the coarse integrator over the complete time interval we are interested in, okay? So you go from there, and until the very end, okay? You do that in a sequential manner, but this is not expensive because you use your coarse integrator. Now you have this kind of milestone, if you think of the literature of Ron Albert, for instance. You have this milestone along the time arrow, and we are going to use them to build on the trajectory, okay? And of course, we are doing a time decomposition algorithm, so we will proceed in an iterative manner, okay? And so this was the first iteration. Yes?
So for this coarse integrator, typically, the generator, if you take it just a fine guy, stability will be.
So I will spend a few slides. In a few slides, I will explain what choice we make for MD. Okay. Because for MD.
Or any very fast system like.
Okay. So if you have a fast system, the fine integrator, for instance, would be the integrator at the fine scale using a tiny time step, and the coarse one may be, for instance, an integrator of the coarse dynamic that you would guess. Okay, but this is.
So it will be something totally different. Like you make a guess for the coarse.
Yeah, this is not what we're going.
Give some examples.
I'll give some example later on. And if I don't answer your question, then we can chat again. Okay. Okay. So we have this initial trajectory here. And we're going to iterate. So there are two indices. There is the time indices n, and there is the iteration indices k. Okay? We're going to iterate. So we have these black points here. And from each of these black points that you are going to propagate the system, but only over the time range capital delta t, both using the coarse propagator, these are the blue arrows, and the fine integrator, these are the red arrows. Okay? And you do that in parallel over all your time intervals because you already at that stage have all these black points. And so you keep busy, two processors on that interval, two processors on that interval, two processors on the next, and so on and so forth. Okay? So the algorithm is really made under the spirit that you have a huge computer, and after all, this is the spirit of this program also, and that you have many processors that you can keep busy. Yep.
Very quick. So you're propagating with the coarse dynamics and then reintegrating each time step with the fine.
No, here I've got this point. I propagate it according to the coarse dynamic.
Yeah.
I propagate also this point with the fine dynamic.
I mean, from the first point, so it looks like
on the first point, this blue arrow here end up here because at the very beginning I have decided to build my initial configuration with the coarse propagator.
Right. Yeah.
Okay. Yeah. But this is actually the first iteration is just a choice. You may do something else. Okay. But in that spirit, then you would have the blue arrow ended up here. Okay. The red arrow does not, of course, because it is a different integrator, and so you may compute the jumps, which are all these green things, these green gaps, okay, between the endpoint of the fine propagator and the endpoint of the coarse propagator, and you do that everything in parallel over all your intervals, okay? So if you count in terms of whole clock time, and if you count in terms of only the fine integrator is expensive, at that stage you have paid 1 unit of cost, okay? Because each processor has propagated 1 time the fine propagator. You have all these jumps in green, you store them, and next there is a correction stage, which amounts to say, I start with the initial condition here, I propagate according to the coarse, this is the black arrow here, and I add the jump. I find my new iterate here, that I propagate according to the coarse, I add the jump, okay? So this is a sequential part that only use the coarse propagator and add the jumps at each time, okay? That you have pre-stored. Okay. And this will be then your new iterate, your new black points, and you are going to iterate over and over again until you reach convergence, okay? This is the idea. And the fine solver, it's pretty clear, the fine solver is only used in the parallel part of the algorithm, and everything that's done sequential is only built on the coarse propagator, and we assume that it costs nothing. Okay, so you have a very nice feature that if you look at some time instant n here, and if you iterate at least n times, you end up with the exact solution. Okay, and it's pretty clear from the very beginning here that after 1 iteration, this guy is going to be correct. Okay, and this propagates in the system. So if you have n time intervals, and if you do k is equal to n iterations, you are good, you have the exact solution. But of course, then you would have paid exactly the same amount as the fine propagation from the very beginning. Okay, so this is nice, but this is not practical. What happens in practice is that actually convergence is reached much sooner. Okay, and so the number of iterations that you need to get a convergence until the time n is way, way smaller than n. Okay? And so in a few moments I will define what the gain is, but you already have understood that the gain is going to be the number of time step of time interval here, because that would be the cost of the fine propagation from the very beginning, divided by the number of iterations that I needed, because this is also the unit of cost. Okay.
Can I ask a question?
Sure, please.
So how does the stability of this hybrid algorithm relates to the stability
So
of the fine algorithm?
Okay, so of course we assume that we have made the fine and the coarse propagator stable, for sure. Okay, but even in that case, there may be lots of trouble. If you think, for instance, of Hamiltonian problems, the energy is not conserved at all by this thing. And here what we're going to see in the simulation with the Langevin equation is that if you go for long times, then you will be not stable. Okay, and this is all about making it stable, this work. Okay, so this is not, I mean, the fact that you have 2 elementary blocks that are stable is not enough to make the whole algorithm stable, for sure.
So let me just,
Sure.
I mean, maybe, are you kind of like building a Picard iteration with a larger convergence interval? That's sort of what you're kind of building here?
Yeah. You may iterate, yeah. You may think of this also as, okay, so the system is nonlinear, so I'm going somehow to solve it with a Newton scheme, and to compute the gradient of the Newton, I'm going to use a coarse solver. So it's like a quasi-Newton algorithm. You may also think of it.
Basically, you're reducing your Lipschitz constants to large, yeah.
So we'll see with the stability in a moment. Yeah. Okay. All right. So this is nice, but now if you think of it in terms of molecular dynamics simulation, there is a little catch in the sense that the reference computations are usually done with a time step which is already quite big, and you have not so much room to increase it. Okay, and so you are very close already to the stability limit. Okay, so there is no room to define a coarse propagator in that setting. So we are going to change gears a little bit and to say, okay, our 2 propagators are going to use the same time step, but for different force fields. Okay, and the cost difference will come from the fact that the force fields, one is basic and the other one is very expensive. Okay. So we have our Langevin equation sitting here and there. And so the fine propagator is the integration of that dynamic with the reference force field here, whereas the coarse propagator is the integration of the Langevin dynamic with the coarse propagator here. Okay, and the cost difference will come from the fact that these two guys are not as expensive to evaluate one with each other. Okay. We are coming from the ODE deterministic world, and so the noise that we put here for the fine propagator is identical to the noise that we put on the coarse thing. Okay. With the idea that we are looking for trajectorial convergence, and so in that case, this is needed. Yes?
So if I hear this right, you're doing a model coarsening rather than
I do not do model coarsening here.
because you're saying you have a coarse.
Yes, it's a coarse potential in the sense that, okay, in a minute, in the end, in the last part of the talk, this guy will be EM, and this guy will be SNAP, but the number of atoms that you're manipulating is the same for both models.
And the same steps also in both integrations.
Yes, exactly.
So you're now getting your gain somewhere else.
Yeah. Okay, and we have chosen to work with the idea that this guy and that the guy make only one time step advance of this dynamic. Okay, but there are other choices. So there is only one numerical parameter in terms of the time, which is this delta t, which is how far you go before you synchronize somehow. Okay. Okay. Yes.
So VC and VF, the two guys, VF and VC, you're saying their fundamental frequencies are the same?
No.
Yeah, right. Okay.
They're not.
So,
But I picked. If your question is about stability, I picked a time step here such that both of them have stable integration. Okay. So if I was running only that guy, it would be stable. If I was running only that guy, it would be stable. Okay. So two toy models. One of them is really a toy model, but this is helpful as well to understand things. We picked a quadratic model as a fine potential, q²/2, and to mimic the traditional situation that you have a coarse potential, which may be a bad description of the fine, we picked as coarse potential another quadratic potential with a different frequency, omega. Okay? So this is just a mathematical game to play with the parameters. It is nothing close to anything applied. Okay? Another system, which is a bit more complex, is a Lennard-Jones system in 2D. So there are 7 atoms. This is the most stable configuration, the bottom of the well. Okay? And so the fine potential is the full plane Lennard-Jones description. And the coarse potential here is the harmonic approximation of that guy at the bottom of the well, okay? That you pre-compute and you work with that. Okay, how are we going to measure errors? We are going to measure errors by looking at 2 different iterates of the Parareal algorithm, k and k-1, and looking at this difference over the complete trajectory. Okay, and we renormalize to have relative error. We need to decide on the criteria to declare convergence. Okay? And we are going to declare convergence when this relative error is smaller than the tolerance. And in this first part of the talk, we pick that number. Okay? And again, the gain, so it's a wall clock gain. It's not a computational gain, but the wall clock gain is this n divided by k bar. K bar is the number of iterations to reach this guy. N is just the cost that it would have of the fine propagation from the very beginning, and k is the cost paid by each processor because you have made k iterations, okay? And they are all done in parallel. Okay, so let's look at the stability kind of result, okay? So what I plot here is the true error. It's not the error between 2 consecutive guys, it's the true error. here, this is a pretty short trajectory. N is 200. Here is N is 3000. There are various curves here because it corresponds to various values of gamma, the damping parameter. And as you could expect, the larger gamma is, the better it works because the more stable already the problem is. Okay? But in many applications, you as a numerical analyst do not have a handle on the gamma. It's given to you and you have to work with that one. If the trajectory is short, N is 200 here, the error decreases when you iterate. Okay, so the more you iterate, the more you pay, the better, the smaller the error. Okay, so far so good. But now, if you increase the length of the trajectory, you see that this is not the case anymore. When you iterate more, you may have increase of the error. And the error may go to numbers which are completely crazy, okay? And if you are using LAMPS, for instance, as a software, it will, of course, not go there because way before it will tell you, I don't know what you're doing, I stop, okay? And it declares lost atom, and this is it, okay? For sure. So here you have a gain more or less of 10. If you count, you need 10 iterations instead of 200, okay, so 10 or 20. And here the gain is much smaller, first point. And second point, you go to crazy regions. Okay. Even though, for this problem, this is just the harmonic thing, right? So there is no issue of different wells. It's just you have one single well and different frequencies. Okay. I'm sorry? K is the number of Parareal iterations. Okay. So, of course, if you draw this way to the right side, you will end up with convergence because this is built in the algorithm. But the wall clock gain will be 0. Okay. So now if we look at the gain here, so we look at which k-bar we declare convergent, and at this k-bar we compute the gain. This is the gain as a function of n here, again for the harmonic system, for various values of gamma. These are the same as before. And we see that if the trajectory is long, then the gain goes to 1, which means you paid as much as you would have paid, so it's completely useless as an algorithm, okay? And of course, I mean, again, the higher gamma is, the better you are. But in any way, if you look at long trajectories, the algorithm is doomed because it will end up with a gain which is equal to 1. Of course, all these pictures depend on how far the coarse model or the coarse propagator is from the fine model. So this is this picture here as a function of omega, which measures, this is the frequency, the fake frequency of the coarse model, okay? So the real one is 1, okay, on the reference model. And as omega departs from 1 and gets here smaller, then the gain becomes smaller, okay, as expected. You are trying to use a model here which has nothing to do with the reference model, and so you have to pay a price, and the price is the gain goes to no one. Okay. Okay. How far? All of this is amenable to numerical analysis on a very simple case, which is x dot is minus x, so just the gradient of the coarse potential, and x dot is minus the gradient of the coarse potential. So you would have noticed that I went to overdamped, okay, not Langevin, overdamped Langevin, and I erased the noise and just look at scalar problems. So this is extremely limited analysis results, but this is what we can do, okay? And what it says is that, and this is already clear on the other model, is that there is a nice interplay between the length of the trajectory you would like to consider and how far the model are, which is encoded here in this variable, okay? And somehow, if the model are far away, but you don't want to go too far in time, that's fine. If you want to go far, but you have a good preconditioner, this is good as well. And if you are in the classical situation when this is large because the coarse model is bad and you want to go very far, then you are in a bad shape. Okay? And everything can be quantified. And okay, I'm going maybe to skip this in the interest of time. But on this simple case, it could be quantified. And the conclusion, the qualitative conclusions that you get from the analysis are very similar from what you observe on the more complex problem. Okay, so it tells you something on the more complex problem. Okay. So now we want to go.
Maybe quickly.
Sure.
So if you get weighted Hamiltonian, you just have complex exponentials.
I'm sorry?
You turn it Hamiltonian, you just get complex exponentials. Why does that change the analysis?
Because you.
I mean, long-term behavior is I grant you that.
For the analysis, probably. Yeah. That could carry over. Probably. Yeah. Yes. But at some point, we use that there are matrices which commute, which is true in the 1D case, of course. Okay. And so this is, of course, also why it's difficult to go to the Langevin, the purely Langevin case where you have these two variables. Huh? Okay. So it's a limited analysis. Okay. Yeah. That's it. So the idea of making the algorithm adaptive is to build on this kind of result that says if you go for short times, this is good. And if you go for long times, then you go into issues. Okay? So the idea is the following. So we are manipulating the relative energy, the relative error, I'm sorry, E, between two consecutive trajectories, which is a kind of guide that you have a handle on in the numerical simulations. We want to compute on this big time slab. Okay? We run the Parareal algorithm, and we look at the relative error E. First case, it goes below the threshold, the green threshold. We are in the good situation. We have converged. Wonderful. Bad case, which is often the case, the situation, you go over an explosion threshold, delta x. Okay? So these were exactly this case here where you go over whatever reasonable threshold you have decided. So the idea is in this blow-up case, and for the Parareal iteration k on which you have this blow-up, we are going to monitor along the time trajectory the first moment where we indeed go over this blow-up threshold. Okay? So we know that at this Parareal iteration, and for the full trajectory, the error is very large. And now we just investigate along the trajectory that we have already computed when we indeed reach this blow-up threshold. Okay? And that will give us a time moment, M1 here, at which it is reasonable to stop because we know that if we go beyond that, we will go into trouble.
Very good question. Relative error, you mean between one another or between like or
between one iteration and the next?
Like compared to the benchmark or compared to like
that? Okay, so we have the iteration k, we have the previous iteration k minus 1, we average in time, that's the time index, and we divide by the previous one. Okay. So that's something that you have in the computer. Okay, so that gives you a moment where you need to stop. And so instead of trying to compute on the full time interval here, we decide to go on this more conservative time interval, okay, to go less far away. We try to converge the trajectory on this, and so maybe as you pursue the iteration of Parareal, you will still have blow-ups over that, and maybe you will have to decrease again the size of this time interval, and this is done automatically by the algorithm, okay? Until at some point, you will reach a time slab on which you have convergence, okay? Then you have the solution at this moment, and then you start all over again on this new time slab, okay? So this is like reintroducing back some sequential ideas, where instead of going until the time n, we go to some smaller one, we do our job there, and then we start again. Okay? Okay, so there is a choice of the blow-up threshold here. That, of course, if you choose it large, it means that you never stop the algorithm somehow, and so you're back to the vanilla Parareal. If you choose it very small, then it means that you cut all the possible parallelism of the algorithm because you stop as soon as it moves. And so there is no parallelism anymore, so you do not blow up, you do not gain anything, and so the optimal choice is somewhere in between. And what we have seen in the numerical simulations is that more or less the algorithm is not that much dependent on the value that you pick. Okay, so there is like a plateau of good values. So these are the gains for, again, the harmonic problem here, and these are the gains for the Lennard-Jones, where we have exactly the same algorithm. The classical Parareal algorithm are these purple dots, so they sit here, okay? And again, as you look at very long trajectory, the gain goes to 1, the whole clock gain goes to 1. And now, if we implement a blow-up threshold here, for some values of the threshold, we have a much better gain. Okay? So although we reintroduce back some sequential part, in the long run, we make a much better job than the vanilla version of the Parareal. And the gain appears to be more or less independent of the length of the trajectory that you have, which is good because you want to compute far away. All right. And this is essentially it for the toy models, okay? And yes, one last word on the toy model. You may say, okay, we are in the molecular dynamics framework. So in many applications, we don't care about the trajectory. We care about the statistics of the trajectory, okay? Absolutely. But if now we are in this kind of areas, the trajectory are completely wrong, but the averages are going to be wrong as well, okay? So it does not, I mean, the change of setting does not prevent you from trying to adapt the Parareal algorithm. Okay. Sure.
Because you have to store the history for this adaptive scheme.
You store the history, you only have the k-1,
But if I have to shorten my block size to m,
if you have to decrease then if you have to decrease you mean storing in time or storing in
storing the trajectory history to be able to.
Yes, yeah. But you don't have to store in terms of Parareal iteration, because if you decide at some point to make the interval shorter, then everything that you have computed on this small thing is still valid. And so you can proceed with the iteration, okay? But in terms of yes, in terms of, all right. So what we wanted to play was to adapt, I mean, to exactly use the same algorithm on a more realistic problem. And this is joint work with Danny on the simulation of self-interstitial atoms in tungsten. Okay, so we have a 3D lattice here of tungsten atom. These are these light red atoms here. And we insert in that lattice, and this is the dark red atom here, which is barely visible, we insert here an additional atom. Okay? So it will sit somewhere in between the atoms of the lattice here. It is a defect. And what's going to happen is that the defect will migrate from one place to another one, from one well to another one. Okay? So it is a metastable system. And we are playing with parameters such that, one, the system is metastable, so the interstitial atom here stays for a long time before hopping. And two, it is not that metastable in the sense that on on trajectories that we can compute, we may see several jumps. Okay? This is also the reason why we consider a self-interstitial atom and not a vacancy, for instance, because a vacancy hops much less often, and so it will be very hard to see many events. Okay? And so here, the quantity of interest are residence times. Okay? Okay, so on that example, what are the potentials? So the coarse potential, I told some moment ago, the coarse potential here is going to be an IPAM potential. And the fine potential is going to be a SNAT potential with many parameters, and we already heard in this workshop about this potential. Okay? The cost ratio between the two is a bit more than 2,000. Okay? And you need to have some room between the two cost of the VC and VF in order to have some gain. Okay? So evaluating with the fine potential is 2,000 times more expensive than evaluating the coarse potential. What we did, or what Olga did actually, was to do a non-intrusive implementation. So we're going to use lamps, but we don't want to implement stuff into lamps. We use it somehow as a black box. Okay? So the time stepping is performed within lamps, but the Parareal algorithm is implemented in a Python routine or above lamps, okay? So all the plus and minus and so on are done in Python, and at some point Python calls lamps to advance the system either according to EAM or to the snap potential, okay? Actually, this creates difficulties because the time stepper of lamps is built under the assumption that you are going to do many time steps. Okay? And in that regime, it's perfectly fine. But here, we are not going to do that because we are going to do one time step, then we do the plus minus of Parareal, and then we start again, and so on and so forth. Okay? And in that regime, there are particular issues that we have discovered first and then fixed. And so if you want to talk about it, that's offline discussions. Okay? But that was pretty fun. All right. And everything is available on everything, which means the Python routines are available on the GitHub of Olga. Okay? So first, we may look at the trajectorial accuracy, which means here that we have here the reference residence time. What is it? I have an initial condition. I follow the Langevin dynamics with my reference potential, and the defect is going to stay 122 time step in a well before jumping to another one. And in this another well, it will stay 23 time step and then jump to another well and so on and so forth. Okay? So these are in units of the time step. Okay? These are the reference expensive computation. Now we play the game with Parareal, and since we are after here a trajectorial accuracy, which is to reproduce the time that we spent in a well on really that unique trajectory, what we are going to do is to work with the convergence criteria, which is extremely small. Okay? The trajectory are chaotic, so if you allow them to get about a little bit one to each other, this is it. This is the end, and there is no way to fix it. Okay? So this is why we implement here a very small criteria to declare convergence. And if we do so, then the list of residence times that we observed on that Parareal trajectory after convergence is, at least for the first ones, identical to the reference.
So these are exit times from different basins, as I'm
indeed, absolutely. As you follow the trajectory.
It's just one trajectory.
It's just one trajectory, absolutely. Absolutely. Okay? At some point, you diverge because the trajectory is chaotic. Okay? And of course, if you want to get that, so this is one single trajectory fed with the same Gaussian increment, started from the same initial condition, of course. Okay? Otherwise, it's just nonsense. And if we play with larger convergence criteria here, this is doomed from the very beginning because the trajectory are too different one from each other. Okay? All right. So that's nice, but it is also a bit demanding in the sense maybe you are not that interested into the particular list on a given trajectory. Maybe you are more interested in the statistics of the residence time. Okay? So we are going to play that game now. And because we are after statistics, all the trajectories that we are going to consider are fed with different Gaussian increments. We start with different initial conditions. So all the trajectories are different. Okay? So these are the reference results. This is the histogram of the residence times that we see. Again, they are measured in the unit is not the femtosecond, but the number of time steps that we have spent. And the time step, by the way, is 2 femtoseconds on that system. Okay? And the temperature is close to 2000 K. And so this is the histogram of the residence time. We've seen here more or less 300 exit events. Okay, and now if you average all these times over the 300 exit events, this is the number that you find. Okay, so this red curve here is just the average over more and more exit events. Okay, and we go there because we cannot afford more than that. Okay, if you want to see more events, you need to have longer trajectories. Actually, this is not done on a single trajectory, but this is done on many, many small trajectories because you can perform this everything in parallel. Okay? So this is the mean, and this is the confidence interval on the residence time. We have 300 events, and we may compute also the confidence interval for this mean residence time. Okay? You will notice that the confidence interval is quite large, okay, because the statistics is reasonable but not very rich. Okay, so it does not make a lot of sense to look at things that are more elaborated than just the mean. Okay, and so we didn't look at the distribution itself, for instance, or the variance or whatsoever. Okay, we just looked at the mean because the statistics is what it is. Okay, so these are the reference one, the expensive computations. If you play the game with only the coarse potential, okay, so you forget about the snap potential, you just use the coarse, this is the number that you find, okay? 100 instead of 320. Okay, so you just cannot rely at all on this coarse potential for this kind of computations. Okay, so now we are doing a mix between the two. We are using the Parareal algorithm with the EAM as coarse potential and with the snap as fine potential. Because we are not after the trajectory accuracy, we may relax on the criteria of convergence. So here we work with 10 to the minus 3. For sure, we have no convergence in terms of trajectory whatsoever. Okay. On the top picture, these are the things that we've seen already on the last slides. And these are the Parareal result at convergence. Okay. And the mean is that, and the confidence interval is that. Again, we see something like 350 events. Okay. So this confidence interval is computed over these 350 things. And what we observe is that the two confidence intervals do overlap. Okay, and this is the only thing we may ask for. Okay, and so because they overlap, it means that the Parareal results are accurate in the sense they are consistent with the reference result. Okay. The gain that we have on this computation, so this says that we are doing an accurate job. And the gain that we obtain, the number of iterations, and if you divide by n and so on and so forth, you find a gain which is somewhere between 5 and 20, depending on the time steps you are going to use. And the more aggressive, the bad thing is that the more aggressive you are in terms of time step, the smaller the gain is. Okay, so if you play a game with 2 femtoseconds, you will have a gain which is close to 5. But if you play the game with 0.5 femtosecond, because you want to be very conservative on the computation of the trajectory, then you will have a gain of 20. Okay? On the other hand, the gain does not depend too much on the parameter delta conv and the blow-up parameter. Okay? They are pretty stable. Okay, okay, so I think, yep, good. That's a good timing. So we've seen that it's possible to play the game of the Parareal algorithm with on a realistic example that we have computed with lamps. One thing I want to underline here is that in the end, the gain that we obtain for this system here are close to the gain that we obtained for the Lennard-Jones case, which was a much smaller system. Okay, so this was 7 atoms in 2D. These are 129 atoms in 3D, which seems to say, I'm not going to bet on that, but it seems to say that the gain is more or less insensitive to the complexity of the problem, okay? Or at least that's the hope. And this is consistent with that hope, okay? And with this, I would like to thank you.